Hello everyone, welcome back to the latest lecture session. We've been looking at, I believe, water quality parameters for quite some time, then moved on to looking at water treatment. In that context, we looked at home water treatment devices because of relevant issues and because most of you are also going to face such issues, let's say. And obviously, we want you to take a knowledgeable decision out there, right? And then we generally looked at general water treatment plants typically run by the government or private agencies, and we saw that we typically try to let the colloidal particles or the bigger particles that can settle down. If not, we use coagulation to neutralize the charge and flocculation to let the particles come together. So once these colloids come together, you are going to have flocks formed which are heavier and they are removed, and then you will have sedimentation, I guess, right. So let's move on and look at reverse osmosis, because people are selling us as if it was a solution to all water problems. Let's look at this in greater detail. So though I have the title referring to home water purification system, this is, as you will see, relevant to a much more wider range of aspects, let's say, right. So here we are, as I mentioned, people are not knowledgeable, and if cost permits, people typically go for RO units, let's say, right. That's why I say most. And the issue is that high capital and maintenance costs. If you remember, we have an RO unit. Obviously, for that you need a pump. It obviously costs a lot, let's say, right. Electricity costs and also the RO membrane, let's say, is going to be pretty high. Pump and RO unit, let's say. So high pressure is required to drive reverse osmosis. It's not osmosis. Let's say if I can try to give an example, let's say people washing clothes, let's say, or people helping their mothers in cleaning the utensils, or let's say you have what is this solution with high total dissolved solids, let's say, or take a glass of water, mix salt in it and put your hand in it for quite some time. What do you see? You see your fingers, I guess, out of shape or so, if I may say so. Well, I would assume, or I would think that it's because water is leaving your system and moving into the system where the TDS is high. It's osmosis, I guess, right. The system wants to decrease the chemical potential, let's say. Or in general, people say you should not drink seawater. Let's say if you are stuck, if you are on a boat and you are stuck out there and you have no access to water and you are in the sea, will you drink seawater or will you try to distill it and then drink that water, let's say, right, distilled water, let's say, assuming you are able to do that. Why won't you drink seawater? Obviously, pathogens and suspended matter, so on and so forth, but you can filter out, and pathogens, let's say if you are dying of thirst, are not your primary concern, right. So what are we concerned about? The issue is that you have remarkably high salt concentrations there, 30,000 milligram per liter, 30 grams per liter total dissolved solid, right. Salinity is obviously pretty high, or much more than 30 grams per liter. So if you take in such salt water, the water is not going to enter into your cell membrane or such, your system can't use that water. But what's going to happen is the water from our body or the cell, let's say, is going to move into this seawater, let's say, right. So the body will end up feeling, or losing water and feeling more thirsty again. So general aspects, if I am erroneous in my analysis and if anybody finds information that tells you that this example, I guess, is not a good example in this context, just let me know. But again, these are typically worthwhile examples. So again, that's one aspect, I guess, why, it's osmosis, right. When let's say you have high chemical, high TDS here, and let's say this is a water container, and you have high salt concentration here and less salt concentration here. What is going to happen? The water is going to move from here to here and to try to decrease the chemical potential out here. It's a semi-permeable membrane here, right, osmotic membrane here. But for reverse osmosis, what is it that you want it to happen, let's say, right? What do you want to happen now, right? You want the reverse to obviously happen here. Fine, so osmosis, right, this is what you have. But then then you are going to have more concentration here, and I guess lesser concentration in this high TDS zone, but not less enough obviously for you to be able to use the water. So this is osmosis, but then you want the reverse to occur. So, for that obviously you need to apply external pressure, let us say, to beat that particular driving force due to the difference in chemical potential, let us say. Again, what do we have here? So, another aspect is, as you see, whichever way, even reverse osmosis and such, let us say, if I push it from, let me see if I can erase it. In reverse osmosis, let us say, if I am able to push the water from this high TDS zone to low TDS zone. So, now I will have much more purer water here, right, and but as you can see here, you will still have, or as water moves from here to here, what will you see? You will see that the concentration here, right, is going to increase, and thus has to be bled out. This is the reject water, right. So, you would have seen that, let us say, if your RO units at your home are like this, installed and plugged in here, and water comes in, you will always have a bleed going into the sink, right. You will have a bleed pipe going into the sink, and whenever you use your RO water to take some water out for your usage, you will see that you are also bleeding water out into this sink. What is that? This is that high TDS reject water from the RO unit, and as mentioned, sometimes it's the reject water is as high as 50%, and if the RO unit is not functioning well, it can even go to 80% or obviously higher, let us say. So, we have to put in a lot of pressure, which means more money and energy, right, and also we have to deal with high TDS water going into the environment, let us say. So, these are the issues of concern obviously, right. So, that is something to keep in mind. So, considerable wastage of high TDS water as reject, and obviously because let us say you do not want your membrane to be, I should not use the word clogged up, but should not be fouled, you are going to have micro and ultra filtration before the RO unit. So, to improve the life of the RO. This is what the entrepreneur did not do earlier. Again, hopefully you are more knowledgeable now. So, again, osmosis, a relatively better picture. So, osmosis is the net movement diffusion, I guess it is obviously due to diffusion of a solvent. Okay, we are talking about the salts, but you will have a membrane that does the other, I guess, does not prevent solvents to move. Anyway, that is with respect to reverse osmosis. Let me get back on track. Osmosis is the net movement of a solvent from a region of higher water concentration to a region of lower concentration, right. And what do we have here? Let us say we have what is this now? Lesser solute and more solute here, or let us say water with high dissolved concentration, pardon me, that is the reverse, water with low dissolved concentration, water with high dissolved concentration, right. So, osmosis, what is going to happen? This is what is going to happen. Water is going to travel from this chamber, diffuse through, and you are going to have, or the system is going to achieve equilibrium, let us say, right. And that is what you see here, but obviously this will not solve my purpose, because I do not have the pure or clearer, not clearer, purer water or low TDS water that I want. But what are we doing with respect to RO though, right? Reverse osmosis is the net movement of solvent from a region of higher salt concentration to a region of lower water concentration. So, it is the reverse of osmosis. So, how does this occur? Feed water, let us say, that is what you have, right, coming in from your groundwater or sometimes surface water, and this is going through, and your concentrated reject water is going to be bleeded out. This is your reject, let us say, with higher TDS, and this is your permeate, which you are going to use or which you are going to drink, right. So, that is something to keep in mind. So, obviously, let us look at what else is required. So, let me start from what do we say, the bottom out here. First, microfiltration, pressures required are less than 1, and what can it remove? So, let us say we have a collection of different what do we say, variables that I do not want to have in my final water, or the magnitude of this variable has to be low in my water. So, what can microfiltration do? It can, I guess, remove or reject bacteria and some fat and proteins. Again, all this is based on size, let us say. The pore size is 10 power minus 1 to 10, right, 0.1 to 10 micrometer, let us say, that is the pore size. With that, obviously, we are able to remove bacteria and some proteins. And I guess ultrafiltration, okay, I guess I slightly misread the what do we say, graphic out here. Bacteria and fat or bacteria will be removed and the others will go through, And then one order of magnitude lesser, we are having ultrafiltration, obviously because the size of the pore is less, greater pressure, again meaning higher costs obviously. And so what else can it remove? I guess proteins. And the next one is nanofiltration. So again another order of magnitude lesser in size, so again pressure increases. And I guess different types of compounds here, lactose. And then I guess what do we have with respect to RO, let us say. What does RO reject? It rejects even dissolved salts or ions, right. That is what you see here. RO rejects everything out here, and you just have the water going through. And the issue is that if you do not have pre-treatment by these systems or a combination of at least two of these systems, you are going to have what do we say, choking up of your particular RO membrane and fouling. And obviously as you see, the pressures required are very high, and obviously that is because the pore size is pretty low. And obviously now you are going to have what do we say, considerable maintenance issues, let us say, right. Again 1 bar 100 kilopascals, and I guess that is good enough out here. Again, right, bacteria and such, as we can see here, microfiltration range, right, bacteria, ultrafiltration range, nanofiltration, there is some overlap, but with RO or reverse osmosis, the dissolved salts can be relieved. But again, as I mentioned or discussed earlier, is that really required? Not really. So reverse osmosis recovery, I guess, right, RO systems typically run anywhere from 50 to 85% recovery, but this is high, depends on how well you are running your system, but rarely will we reach 85% recovery. Considerable wastage of water during daily usage of water purification systems in your homes, because it bleeds a lot. You see the bleed pipe and the water that you are going to reject, I guess. And as we discussed earlier, for most of our ground waters, or even for let us say treated surface waters, do you need to remove your dissolved solids, and is that an issue? Because TDS in the reject waters is 35,000 ppm or higher based on the type of influent water. But let us say if your influent water TDS is less, obviously your reject will not have such a high what do we say, salt concentration. But I guess the point I should have made here, which we did discuss earlier, was that groundwater, let us say if it is 400 or 450 ppm, right, and you know that let us say there are no such toxic or compounds or carcinogens like arsenic and such, do you need RO? Not really, right. I mean, as we discussed, you just need pre-treatment to remove the suspended solids. You need some let us say activated carbon to take care of organics, let us say maybe in the distribution system or the pipe. And if you are really cautious, you can think of a UV to inactivate any pathogens, that is it, right. And that is pretty cheap, but typically we spend 20,000 and yearly 5,000 if you are really running it well to what do we say, treat your water with RO when it is not required, right. And again, very low TDS water is not good for your health. And again, rejection, I guess 1 minus Cp by Q permeate and Q feed, I guess, right. How much is going through by the feed, and rejects obviously the leftover aspects. So challenges, I mean, just to understand, let us say why this is not good, and because this occurs a lot. So scaling and fouling of membranes occurs, as in scaling you have let us say sulfates or sometimes carbonates, and you will have what happens is, as the compounds come to the surface of your RO membrane, what is going to happen, the concentration here in this vicinity, let us say of the what is this membrane, is going to be very high, let us say, because that is where you have the reject. And if it is very high, obviously the equilibrium constant, it is going to see to it that you are going to precipitate out when Q is far greater than K, ion activity prod far greater than K. What are you going to see? You are going to see precipitation. So that is why you see scaling, and this happens a lot. And fouling of membranes, again different reasons, I guess, right. So that is why lower than desired permeate, right. So that is what you see over time. As fouling occurs, the product water is going to start decreasing for a given pressure, or let us say a lot of pressure is going to be required, let us say, right. So that is something to keep in mind. So one case study that I wanted to, or not case study, one study that I wanted to draw your attention to is the use of RO plants for general water population usage in Chennai. So seawater has TDS around 35 grams per liter or 35,000 milligrams per liter, and RO unit will bring this down to 200 ppm. Let us say if it is 35,000, then it can bring it down to 200 ppm. if an effective again, right. Years of water crisis in Chennai, let us say, saw the government set up 2 desalination plants, right, 2 desalination plants based on R.O. between 2010 and 13. Let us look at the costs and the relevant variables. Each supplies 100 million liters, million is 10 power 6 liters per day, right. You see that is quite a lot. Again, keep in mind, for per person, typically we say that it is 120 liters per person is the requirement per day, fine. In India, depending on the what do we say, economic status of the person, it is either higher or lower, but again 120 is a decent number. Together they meet about 1/4 of the city's water requirement of 830, I guess, fine. City's water requirement is 830 MLD now, and the authorities are planning to install 2 more plants, right. One is 150, which will be operational by 2021, and the other at 400 MLD capacity. But please look at the cost. One is 1260 crores. Again, government agency, when we say funded, it is not obviously what do we say, donation, it is a loan, right. And 4,000 crores again funded or loaned by the Japanese or Japan International Corporation Agency. 4,000 crores for 400 MLD and such. So again, you can typically, high desalinated water has a TDS of, not highly desalinated water has a TDS of less than 50 milligram per liter, right, and is pure in general sense or relative sense, but it does not taste like water, because what gives water its taste, right, its taste, it is the ions that are in it. And if you remove all the ions, and most of which are, let us say, required by the human body, that is obviously not water in the truest sense, because that is not what we require again. So it does not taste like water. And as we discussed earlier, anything 100 to 600 milligram per liter is considered as good quality water, but BIS standards for drinking water, they set it at 500 milligram per liter for TDS, but 100 to 600 is very much acceptable, let us say. So desalinated water removes vital minerals such as calcium, magnesium, zinc, sodium, potassium, and some carbonates too. Again, all these are required by the human body, right, for different purposes, for metabolism too. Yes. So what do most RO plants do? Again, including the ones in Chennai, what do? They put the water through a post treatment process whereby salts are added to make the TDS come back to an acceptable value of 300 milligram per liter. So there is one catch, you need to put in a lot of energy every day to push the water through this RO membranes, let us say, right, high pressures, I think 30 to 60 bar is what we saw earlier. And you also need to be concerned about your scaling on your membranes, that is an issue. To prevent scaling, you add, what do we say, different agents which are typically toxic when released out into the relevant what do we say, environment. Where does it go? Everything into the environment, right. So these are some issues we have looked at, but more importantly, even think of the capital cost. It's what is it, I think 4,000 crores for 400 MLD. So 10 crores per for 1 MLD, and that is a remarkably high cost, right. And what else do I have here? And since they have started functioning, the fishermen, in the region where the reject water is being dumped, okay, I do have that here, complain that the brine being deposited along the seashore, brine meaning let the reject water from the RO plants, let us say, that is what is the brine that I am referring to here, along the seashore is triggering changes along the coastline, not just changes, massive havoc, if I may say. So the changes that we are referring to is massive havoc to the aquatic life there along the coastline, and reducing the availability of prawns, sardines, and different kinds of, I guess, fish here, right. So hypersalinity, why is that? Hypersalinity due to this brine, this brine has remarkably high TDS, God knows, maybe lakhs of TDS maybe, along the shore, affects plankton, which is the seafood of several of these fish species. Again, we are messing up with your what is it, aquatic ecosystem, and I guess the one direct effect is that the plankton which are eaten by the fish, they can't survive in such highly saline water. Keep in mind that these plankton can survive in typical sea level saline water, but the amount of reject saline or brine solution with very high TDS that we are dumping back into the ocean is making that relatively much more salty, and your fish can't survive, right, not fish, plankton. High pressure motors which are drawing in the seawater, suck up small fish, thereby crushing them and killing them again. Again, why is this an issue? Because again, source of protein and livelihood for many hundreds of people, right? It is the fish, and we are slowly but surely killing them, right? We are killing our sources of food, and also ruining the livelihood of hundreds of people now, right? And the only trend that we see is people trying to put up these plants more and more and thinking that they are a solution for every ill out there, which obviously is not the case. For example, IIT Roorkee, I think last year or 2 years ago, a committee and such was set up to look at what to purchase with respect to, or the need for, or what water purification systems were required for the bhavans and such. So everyone is an expert here, right? Every one with no environmental engineering background is an expert. So the first thing they say is RO. Okay, they ended up I guess purchasing RO despite the objections of the lone environmental engineering background person on the committee. Again, this is what we have out there. And do you need RO in IIT Roorkee when you have no other contaminants in the groundwater and your TDS is around 300 or 350, which is almost perfect for consumption? Not really. But again, things work or people behave in weird ways. So on an average, it costs around 900 crore to build 100 MLD plant, okay? And the Chennai experience has shown that it takes 5 years to be set up. To remove the salt required, there has to be a consistent source of electricity, meaning you need energy to for the high pressures that need to be maintained, and again a power plant or diesel or battery source, which again lead to their own environmental costs, I guess, right? Everything is cost. And if you remember, with respect to the CO2 emissions, water and wastewater were, I think, 5th or 6th in the world's top generators of carbon dioxide, I guess, right? Estimates have put this about 4 units of electricity per 1000 liters of water. Therefore, each Chennai plant needs about 4 lakh units of electricity. So it is just the cost for electricity itself, I guess, or I guess I should have been more clearer when I got the data from the article. It is around ₹3 to produce 100 liters of water, which for such a large scale plant is not really sustainable in the long term, let us see. So is it okay? Again, sustainable? Not really. Right, with an average rainfall of 147 centimeters. Again, when I was presenting this info, to general students and such, a colleague of mine, but a person with an air pollution background asked, okay, Banu, you are saying it doesn't work, but then what's the alternative? What do people need to do? They need to drink and they need to survive. That's always the most critical aspect, right? Obviously, an alternative is required. And where to get the water from? The issue is that, as we see, with an annual rainfall of 140 centimeters, Chennai does not need desalination plants. If you look at the input of fresh water, let us say, which are these desalination plants are suited to arid areas with limited fresh water or with limited rainfall, let us say, right. So what can be done, and also there was a relevant issue recently, and that is why I believe the local government bodies also got together and were getting this done. You can restoration of existing freshwater sources, let us say, or sources that can regenerate the aquifer. You have large ponds and such, and people dump construction debris and such, waste management, that is a different issue. And what is happening, all these water bodies, marshlands and such, that act as reservoirs and buffers during flooding, or act as source of water when the water is scarce, they have silted up, let us say, right. People are not letting them thrive, let us say, right. So it is not just a pond of water, it is again everything is aquatic ecosystem out there, right. So what is happening now, all these are either being encroached, and that is why water has nowhere to go. You have flooding when you have rainfall, and all the rain is being sent to the ocean because it is not getting enough time to go into the ground, right. And people do not have groundwater recharge relevant aspects constructed in their houses. It is pretty easy to do, right, relatively highly permeable area with respect to gravel and then sand, and water will go through, right. We are not doing that. And again, all the water that is raining down, we are sending it into the ocean and then spending much more money to wreak havoc along the coastline, and then take this low TDS water and such, right. So I guess you see we are in a self-defeating cycle. The usage of treated sewage is an option, but at least in India, I guess, where people are remarkably prone or remarkably sensitive, rather, let me put it that way, right, would not be very comfortable with drinking treated sewage, but that's where we are going to end up, if not now, maybe 20 or 30 years down the line. So the issue is that let's say water that I consume, we talked about 120 liters per capita per day, right, per person per day. So around 80% of this will be wastewater, given out as wastewater, which has to be treated. So what do you do with the wastewater? If you dump it out in the ocean, it's a loss of resource. But if you treat it well enough, let's say, and either use it for groundwater recharge, but again only well enough, we will discuss this later, or treat it to such an extent, you can reuse it for consumption, if not for direct drinking purposes, if not for consumption, for daily activities. Well, that's where we are going to end up. But again, right now people are restoring some of the existing freshwater sources, but only because they have been facing severe droughts, let us say, and rainwater harvesting and groundwater recharge, let us say, right. Now you are building up everything, let us say everybody wants a polished surface, they do not want grass, they do not want to trample on mud or get mud on their shoes. So water has no place to percolate into the subsurface, and then the groundwater table is going to decrease over time, right. So that is the issue. You want rainwater harvesting, which is pretty easy to do, to allow for groundwater recharge, let us say, right. So again, further reading these articles, I guess, so you can look at that or discuss them. So now we are going to move on to wastewater treatment, but I see that we are almost out of time. So I guess I will end today's session and look forward to discussing wastewater treatment in the next session. Thank you.